Hello everyone. The certification got updated along with that the study materials and the complete syllabus. These has been available in my LinkedIn profile for almost 2 months now, but I never created the YouTube playlist for it. So I'm creating that now. For accessing the PDF, feel free to use my LinkedIn profile page. It should be there in the top link. Thank you.
Databricks Certified Data Engineer Associate Study Guide Overview. This comprehensive study guide covers all topics for the Databricks Certified Data Engineer Associate exam. The certification validates your ability to perform introductory data engineering tasks using the Databricks Data Intelligence Platform, including ETL operations, pipeline orchestration, and data governance. Note: Databricks certification still calls Delta Live Tables, DLT, so for this guide we will keep it that way instead of calling it Lakehouse Declarative Pipelines, LDP. Section 1. Databricks Intelligence Platform enable features that simplify data layout decisions and optimize query performance. The Databricks platform provides several automated optimization features that significantly reduce the manual effort required for data layout and query optimization. Understanding these features is crucial for efficient data engineering. Delta Lake optimization features form the foundation of automatic performance enhancements. When you work with Delta tables, features like auto-optimize and auto-compaction run automatically to maintain optimal file sizes. Auto-optimize ensures that data files written are appropriately sized, typically around 128 megabytes, to prevent the small file problem that often plagues data lakes. This happens transparently during write operations without requiring manual intervention. The platform also implements Z-ordering, which co-locates related information in the same set of files, dramatically improving query performance when filtering on specific columns. You can enable Z-ordering through the optimize command with Zorter by clause, which reorganizes data to minimize the amount of data that needs to be read. Adaptive Query Execution, AQ, represents another critical optimization layer. AQ dynamically adjusts query plans during execution based on runtime statistics, rather than relying solely on static optimization. This includes coalescing shuffle partitions to reduce the number of tasks, switching join strategies based on actual data sizes, and handling data skew more effectively. For instance, if ACT detects that one side of a join is much smaller than initially estimated, it might switch from a sort merge join to a broadcast join automatically. These optimizations happen without any configuration changes from your side, though you can fine-tune the behavior through Spark configuration properties. Data skipping and statistics collection work together to minimize data scanning. Delta Lake automatically collects statistics about data files, including minimum and maximum values for each column within each file. When queries include predicates, the engine uses these statistics to skip entire files that don't contain relevant data. This process, called data skipping, can reduce query times from hours to minutes for large datasets. The statistics are maintained automatically as part of the Delta Lake transaction log, ensuring they're always up to date without requiring manual analyze table commands. Photon acceleration provides vectorized query execution that can speed up queries by up to 12x. Photon is particularly effective for queries that involve heavy computation, aggregations, joins, and data transformations. It's written in C++ and uses modern CPU instructions for vectorized processing, making it especially powerful for workloads that would traditionally be CPU bound. When you enable Photon on your clusters, it automatically accelerates compatible operations without requiring code changes. Documentation, Delta Lake optimization, Photon runtime, optimize command, Z-ordering documentation explain the value of the data intelligence platform. The Databricks Data Intelligence Platform represents a unified approach to data analytics, an AI that addresses the fundamental challenges organizations face with fragmented data architectures. Understanding its value proposition helps you leverage the platform effectively. The lakehouse architecture combines the best features of data lakes and data warehouses into a single platform. Traditional data lakes offer low-cost storage and support for diverse data types, but lack the performance and asset guarantees needed for reliable analytics. Data warehouses provide excellent performance and reliability, but are expensive and limited to structured data. The lakehouse architecture bridges this gap by providing data warehouse-like performance and reliability on data lake storage. This means you can store all your data, structured, semi-structured, and unstructured, in one place while still getting the query performance and data quality features you need for business-critical analytics. Unified governance and security through Unity Catalog provides a single governance solution for all data and AI assets. This eliminates the need for separate governance tools for different parts of your data stack. Unity Catalog offers fine-grained access controls, allowing you to manage permissions at the catalog, schema, table, and even row and column levels. It also provides comprehensive data lineage, showing how data flows through your pipelines and which downstream assets depend on specific tables. This unified approach significantly simplifies compliance with regulations like GDPR and PA, as you have a single place to manage data access and track data usage. Collaborative development environment enables data engineers, data scientists, and analysts to work together seamlessly. Notebooks support multiple languages, SQL, Python, Scala, R, in the same notebook, allowing team members to use their preferred tools while sharing the same data and compute resources. The platform includes built-in version control through repos, real-time collaboration features, and the ability to share results through dashboards and visualizations. This collaborative approach breaks down silos between teams and accelerates the development of data solutions. End-to-end ML and AI integration means that machine learning isn't an afterthought, but is deeply integrated into the platform. MoveFlow provides experiment tracking, model versioning, and deployment capabilities. Feature Store enables teams to share and discover features for machine learning. The platform supports the entire ML lifecycle, from data preparation through model training to deployment and monitoring. This integration eliminates the friction typically associated with moving between data engineering and machine learning workflows. Documentation. Lakehouse Architecture Unity Catalog Overview. Identify the applicable compute to use for a specific use case. Choosing the right compute configuration is essential for both performance and cost optimization. Databricks offers several compute options, each optimized for different workloads and use cases. All-purpose compute clusters are designed for interactive development and ad hoc analysis. These clusters stay running between commands, making them ideal for notebook development, where data scientists and engineers run exploratory queries iteratively. They support multiple users simultaneously and can be configured with auto-scaling to handle varying workloads. All-purpose clusters are best for development environments, data exploration, and interactive analytics. However, they're not cost-effective for scheduled production jobs, since you pay for the entire time the cluster is running, not just when executing commands. Job compute clusters are ephemeral clusters created specifically for running automated workloads. They start when a job begins, run the workload, and terminate automatically upon completion. This makes them highly cost-effective for scheduled idle pipelines, batch processing, and production workflows. Job clusters can be configured with specific instance types and sizes optimized for your workload requirements. They also support instance pools, which pre-warm instances to reduce cluster startup time from minutes to seconds. SQL warehouses. Formerly SQL endpoints are optimized specifically for SQL workloads and business intelligence tools. They provide instant query results through aggressive caching and query optimization. SQL warehouses automatically scale up and down based on query load, ensuring consistent performance while minimizing costs. They're the best choice for serving dashboards, supporting by tools like Tableau or Power BI, and running SQL queries from applications. SQL warehouses also include features like query history, query profiles for optimization, and alerting capabilities. Serverless compute represents the latest evolution in Databricks compute options. With serverless, Databricks fully manages the compute infrastructure, including provisioning, scaling, and optimization. You don't need to specify cluster configurations or manage infrastructure. You simply submit your workload and Databricks handles the rest. Serverless compute is available for SQL warehouses, notebooks, and workflows. It provides instant startup times, automatic scaling, and optimized performance without any infrastructure management overhead. This option is ideal when you want to focus purely on your data and analytics without worrying about infrastructure details. Choosing the right compute depends on several factors. For development and experimentation, use all-purpose clusters with auto-termination enabled to control costs. For production idle pipelines, use job clusters with appropriate sizing based on your data volumes. For SQL analytics and by tools, SQL warehouses provide the best performance and user experience. When you want hands-off operation with automatic optimization, serverless compute options eliminate infrastructure management entirely. Consider using cluster policies to standardize configurations and control costs across your organization. Documentation, compute types, serverless compute section 2. Development and ingestion use Databricks Connect in a data engineering workflow. Databricks Connect enables you to write and execute Spark code on Databricks clusters directly from your local development environment, bringing professional software development practices to data engineering workflows. Setting up Databricks Connect involves installing the library in your local Python environment and configuring it to connect to your Databricks workspace. The setup process requires your Databricks host URL, personal access token, and cluster ID. Once configured, you can write PySpark code in your preferred IDE, like Versus Code, PyCharm, or Intelli, and execute it on remote Databricks clusters. This setup allows you to leverage local development tools like debuggers, linters, and testing frameworks while utilizing the computational power of Databricks clusters. The configuration is stored in a DATABRICKSCFG file, making it easy to switch between different workspaces or clusters. Development workflow integration transforms how data engineers build and test their code. Instead of developing exclusively in notebooks, you can create modular Python packages with proper project structure, including separate modules for transformations, utilities, and tests. This approach enables unit testing of individual functions using frameworks like PyTest, without needing to run full Spark jobs. You can use version control systems like Git more effectively, as Python files are easier to diff and merge than notebooks. The ability to bug code line by line in your IDE, set breakpoints, and inspect variables dramatically improves development productivity and code quality. Best practices for production pipelines include organizing code into reusable libraries that can be packaged and deployed to Databricks. You should separate configuration from code, using environment variables or configuration files to manage different settings for development, staging, and production. Implement comprehensive logging using Python's logging framework to track pipeline execution and troubleshoot issues. Create abstract base classes for common patterns like data readers, transformers, and writers to ensure consistency across your pipelines. Use dependency injection to make your code more testable and maintainable. Testing and continuous integration becomes much more robust with the Databricks Connect. You can write unit tests that run locally against small test datasets, integration tests that connect to development clusters, and end-to-end tests that validate entire pipelines. These tests can be integrated into CI/CD pipelines using tools like GitHub Actions or Azure DevOps. The ability to run tests locally before deploying to the Databricks catches errors early and reduces development cycles. You can also use code coverage tools to ensure your tests adequately cover your code base. Documentation. The Databricks Connect determine the capabilities of notebooks functionality. The Databricks notebooks provide a comprehensive interactive development environment that goes far beyond simple code execution, offering features that support the entire data engineering lifecycle. Multi-language support and magic commands allow you to use SQL, Python, Scala, and R within the same notebook using language magic commands, %SQL, %Python, %Scala, %R. This flexibility means you can use SQL for data exploration, Python for complex transformations, and Scala for performance-critical operations, all in one workflow. The %run magic command lets you execute other notebooks, enabling modular development, where common functions are stored in separate notebooks and imported as needed. The %fs magic command provides file system operations, while %sh gives you shell access for system commands. Visualization and data exploration capabilities include automatic visualizations for query results with customizable chart types, colors, and aggregations. You can create interactive dashboards directly from notebook outputs, making it easy to share insights with stakeholders. The display function provides enhanced visualization for data frames, including profiling statistics and data distributions. Notebooks also support interactive widgets, drop-downs, text inputs, multi-select that create parameterized notebooks for different scenarios without code changes. These widgets can be connected to dashboard parameters, creating dynamic, user-driven analytics. Collaboration and version control features enable teams to work together effectively. Real-time collaboration allows multiple users to edit the same notebook simultaneously, with presence indicators showing who's working where. Comments can be added to specific cells for code reviews and discussions. Built-in revision history tracks all changes with the ability to restore previous versions or compare differences. Integration with Git through the Databricks repos provides professional version control workflows, including branching, merging, and pull requests. Notebooks can be exported in multiple formats: HTML, PDF, DBC, for sharing and documentation. Advanced development features include Variable Explorer for inspecting objects in memory, autocomplete with IntelliSense for faster coding, and integrated debugging capabilities for Python code. Notebooks support background execution, allowing long-running jobs to continue even when you close your browser. The ability to create and manage notebook workflows enables you to chain multiple notebooks together for complex pipelines. Environment variables and secrets can be accessed securely through utils.secrets, keeping sensitive information out of your code. Notebooks also provide access to MoFlow for experiment tracking and model management directly from your development environment. Documentation. Notebooks overview. Magic commands classify valid autoloader sources and use cases. Autoloader provides a robust, scalable solution for incrementally ingesting data files as they arrive in cloud storage, eliminating the complexity of managing file processing state manually. Supported data sources and formats encompass a wide range of file types commonly used in data engineering. Autoloader can process in files, including nested and semi-structured SYN, automatically inferring and evolving schemas as new fields appear. CSV and TSV files are handled with intelligent type inference and support for headers, custom delimiters, and various encoding formats. Parquet files benefit from column pruning and predicate pushdown for optimal performance. Avro, ORC, and Delta formats are fully supported, along with binary files for images, PDFs, and other unstructured data. Text files can be ingested as raw strings for custom parsing. Autoloader works with files stored in Azure Data Lake Storage, AWS S3, Google Cloud Storage, and Databricks' own DBFS, providing consistent behavior across cloud providers. Incremental processing patterns make Autoloader ideal for various ingestion scenarios. For streaming ingestion, Autoloader uses cloud provider notifications, like AWS Squares, Azure Event Grid, to detect new files within seconds of arrival, enabling near real-time processing. In batch scenarios, it efficiently tracks which files have been processed using ROC's state management, ensuring exactly once processing guarantees. The directory listing mode provides a simpler alternative for smaller datasets or when cloud notifications aren't available. Autoloader handles backfilling historical data intelligently, processing existing files before moving to incremental mode. It also manages file modifications and deletions gracefully, with configurable behavior for different business requirements. Schema evolution and data quality features address common challenges in production data pipelines. Autoloader can automatically infer schemas from files, detecting data types, and handling missing columns. When new columns appear, you can configure Autoloader to automatically add them to the target table, add new columns option, fill the stream for manual review, or ignore them entirely. The rescud data column captures malformed records that don't match the expected schema, preventing data loss while maintaining pipeline stability. Schema hints allow you to override inferred types for specific columns, ensuring consistent data types even with varying input data. Merge schema capabilities combine schemas from multiple files, accommodating files with different structures in the same directory. Use cases and best practices demonstrate Autoloader's versatility. For IoT data ingestion, Autoloader processes millions of small SYN files from sensors, automatically handling late arriving data and out-of-order files. In log aggregation scenarios, it continuously ingests application logs, web server logs, and audit logs, parsing semi-structured data and extracting relevant fields. For data lake ingestion, Autoloader serves as the entry point for raw data, maintaining bronze tables in your medallion architecture. It excels at handling vendor data feeds, where file formats and schemas may change without notice. Best practices include using cloud notifications for production workloads, enabling schema evolution for exploratory workloads, setting appropriate trigger intervals based on latency requirements, and monitoring ingestion metrics through structured streaming queries. Documentation, Autoloader overview. Autoloader options demonstrate knowledge of autoloader syntax. Understanding autoloader syntax is essential for implementing robust file ingestion pipelines that handle real-world data complexities. Basic autoloader configuration starts with the readstream API using the cloud files format. The fundamental syntax requires specifying the format of the source files and the location to read from. A basic implementation looks like spark.readstream.format, cloud files. Option, cloud files.format, SYN. Load, /path to source. This simple syntax sets up continuous monitoring of the specified directory for new SYN files. You must specify the cloud files.format option to indicate the underlying file format, SYN, CSV, Parquet, etc. The cloud files.schema location option is critical for production use, as it stores the inferred schema and checkpoint information, enabling schema evolution and exactly once processing guarantees. Advanced options and configuration provide fine-grained control over ingestion behavior. The max files per trigger option limits the number of files processed in each micro batch, helping manage resource utilization and processing latency. The cloud files.include existing files option determines whether to process files that existed before the stream started, useful for backfilling historical data. Schema inference behavior is controlled through cloud files.infer column types, enabling type inference beyond streams, and cloud files.shem evolution mode, controlling how schema changes are handled. For CSV files, options like header, delimiter, quote, and escape customize parsing behavior. The puff glob filter option allows filtering files based on patterns, processing only files that match specific naming conventions. Error handling and data quality syntax ensures robust pipeline operation. The rescud data column option specifies a column name where malformed records are stored as SIN strings, preventing data loss. Option cloud files.rescud data column underscore rescued underscore data. The max filage option ignores files older than a specified duration, useful for avoiding processing of old backup files. The ignore corrupt files and ignore missing files options determine behavior when encountering problematic files. Schema hence override inferred types for specific columns. Option cloud files.schema hence timestamp amount decimal 10,2. These hints ensure consistent data types across different files and prevent type inference errors. Writing and checkpointing patterns complete the ingestion pipeline. A complete autoloader pipeline includes both reading and writing components. Python, Spark.readstream. Format, cloud files. Option, cloud files.format. SYN. Option, cloud files.schema location. / checkpoint schema. Load, / data source. Write stream. Option, checkpoint location. / checkpoint streaming. Trigger, processing time equals 10 seconds. Table, target underscore table. The checkpoint location is separate from schema location, storing streaming query progress information. Trigger options control processing frequency. Processing time for periodic processing. Once for single batch execution. Continuous for low latency processing. And available for processing all available data then stopping. Documentation. Autoloader syntax used Databricks built-in debugging tools to troubleshoot a given issue. Effective debugging is crucial for maintaining reliable data pipelines, and Databricks provides comprehensive tools for identifying and resolving issues at various levels. Notebook debugging capabilities include interactive debugging features that allow you to set breakpoints, step through code, and inspect variables during execution. The Python debugger can be activated using the %bug magic command after an error occurs, opening an interactive debugging session where you can examine the stack trace and variable values at the point of failure. The Variable Explorer shows all variables in the current notebook scope with their types and values, helping identify data type mismatches or unexpected values. Cell-by-cell execution with immediate output visibility allows you to isolate problematic code sections quickly. The notebook also maintains execution history, showing the order and duration of cell executions, which helps identify performance bottlenecks and execution dependencies. Spark AI and query execution analysis provides deep insights into job performance and failures. The Spark AI, accessible from the Cluster Details page, shows detailed information about job stages, tasks, and executors. The SQL tab displays query plans and execution metrics for data frame operations, helping identify inefficient joins, missing broadcasts, or excessive shuffles. The stage details view shows task level metrics including execution time, shuffle read write volumes, and spill to disk, revealing data skew and resource bottlenecks. The Executors tab monitors memory usage, GC time, and task failures across nodes, helping identify out of memory errors and node failures. Event timelines visualize job execution flow, making it easy to spot stragglers and parallel execution issues. Structured streaming monitoring tools help bug streaming pipelines. The streaming query progress dashboard shows metrics like input rate, processing rate, and batch duration, helping identify whether the stream is keeping up with incoming data. Watermark delays and state store metrics reveal memory pressure and late data handling issues. The Streaming Query Listener API allows programmatic monitoring and alerting based on streaming metrics. Checkpoint analysis helps understand stream recovery behavior and identify corruption issues. The ability to inspect the last failed batch's error details and stack traces accelerates debugging of intermittent streaming failures. Log analysis and error tracking centralizes debugging information across distributed systems. Driver and executor logs are accessible through the cluster AI, with filtering and search capabilities to find specific errors or warnings. Structured logging using Log4j allows you to add custom log messages with appropriate severity levels. The Databricks CLI and REST API enable programmatic log retrieval for automated analysis. Integration with external logging services like Datadog or Splunk provides centralized log aggregation across multiple clusters and jobs. Error messages include detailed context about data files, partitions, and row numbers where failures occurred, making it easier to identify problematic data. Databricks Assistant, a context-aware AI assistant that can help you bug your code. When a cell or job fails, the assistant can provide suggestions and explanations to help you diagnose the error. Documentation, debugging in Databricks, Spark AI Guide, Bug Notebooks, Databricks Assistant Section 3. Data processing and transformations describe the three layers of the medallion architecture and explain the purpose of each layer in a data processing pipeline. The medallion architecture provides a systematic approach to organizing data transformations, ensuring data quality improves progressively as it moves through your pipeline. Bronze layer. Raw data ingestion serves as the landing zone for all incoming data, preserving it in its original format. This layer ingests data from various sources including databases, APIs, files, and streaming sources, maintaining the full fidelity of the source data. No transformations are applied beyond format conversion, like converting into Parquet for better performance, ensuring you can always reprocess from the original data if needed. The bronze layer implements data versioning through Delta Lake's time travel capabilities, allowing you to access historical versions of raw data. Schema evolution is handled automatically, accommodating changes in source systems without breaking downstream processes. This layer typically includes metadata columns like ingestion timestamp, source system, and file name to track data lineage. The bronze layer acts as your insurance policy, ensuring you never lose source data and can always reprocess if business rules change. Silver layer. Cleansed and enriched data contains validated, deduplicated, and standardized data ready for analytics and further processing. This layer performs data quality checks, removing or quarantining records that fail validation rules. Deduplication logic ensures each business entity is represented once, implementing slowly changing dimension (SCD) logic where needed. Data types are standardized, like converting string dates to proper timestamp types, and business rules are applied consistently. The silver layer often joins data from multiple bronze tables, creating enriched data sets that represent complete business entities. This is where you handle null values, apply default values, and ensure referential integrity between related datasets. The silver layer implements data contracts, guaranteeing downstream consumers receive data in expected formats with required fields present. Performance optimizations like partitioning, Z-ordering, and creating aggregate tables happen at this layer. Goal layer. Business level aggregates provides curated, business ready data sets optimized for specific use cases. This layer creates denormalized views that align with business concepts, making data accessible to analysts and business users who may not understand the underlying data model. Aggregate tables calculate KPIs, metrics, and measures that power dashboards and reports. The goal layer often implements dimensional modeling, star or snowflake schemas, for optimal query performance and by tools. Different goal tables may represent the same underlying data optimized for different access patterns. One optimized for real-time dashboards, another for batch reporting. This layer enforces business-specific security and privacy requirements, potentially masking or excluding sensitive data. The goal layer represents the single source of truth for business metrics, ensuring consistency across all reporting and analytics. Layer interactions and data flow create a robust, maintainable data architecture. Data flows unidirectionally from bronze to silver to gold, though queries may access any layer depending on requirements. Each layer can be processed with different frequencies. Bronze ingestion might be real time, silver processing hourly, and gold aggregation daily. Error handling varies by layer. Bronze focuses on ingestion reliability, silver on data quality, and gold on business rule consistency. Reprocessing strategies differ too. Bronze rarely needs reprocessing. Silver might reprocess to fix quality issues, and gold frequently reprocesses as business rules evolve. This architecture enables parallel development, where teams can work on different layers independently as long as they respect the contracts between layers. Documentation. Medallion architecture classify the type of the cluster and configuration for optimal performance based on the scenario on which cluster is used. Optimal cluster configuration depends on the workload's specific requirements. Interactive ad hoc analysis. Use an all-purpose cluster with a standard or high concurrency mode, depending on the number of users. Enable Photon for faster query performance, and turn on autoscaling to handle varying workloads and optimize costs. Production-idle jobs. Use job clusters, which are created just in time, and terminate after the job is complete, making them more cost-effective. For critical workloads, use a fixed size cluster to ensure resources are always available, or use optimized autoscaling, which scales down more aggressively when a cluster is underutilized. Use serverless compute for a hands-off, auto-optimized experience. Machine learning and AI workloads. For these workloads, you may need a cluster with this. Databricks offers specific cluster configurations for machine learning, including clusters pre-configured with the necessary libraries. Documentation. Cluster configuration best practices. Selecting appropriate cluster configurations including VM type requires understanding workload characteristics and matching them with cluster capabilities for optimal performance and cost. Memory optimized clusters for complex analytics are essential when processing large data sets with complex transformations, joins, and aggregations. These clusters use instance types with high memory to core ratios, like AWS R5 or Azure E-Series, providing more RAM per executor for caching and processing. They excel at interactive analytics, where data is repeatedly queried, machine learning workloads that require large matrices in memory, and graph processing that maintains relationship data in memory. Configuration best practices include setting spark.sql.adaptive.enabled equals true for dynamic optimization, increasing spark.sql.shuffle.partitions for better parallelism, and tuning spark.memory.fraction based on whether workloads are more cache heavy or execution heavy. Memory optimized clusters reduce spill to disk, improving performance for memory intensive operations significantly. Compute optimized clusters for CPU intensive processing use instance types with high CPU performance, like AWS C5 or Azure F Series, for workloads dominated by computation rather than data movement. These clusters are ideal for complex if operations, string manipulations, SYN parsing, compression decompression, and cryptographic operations. They perform well for idle pipelines with heavy transformation logic but moderate data volumes. Configuration optimizations include enabling Photon for vectorized execution, reducing executor memory since less caching is needed, increasing executor cores to maximize CPU utilization, and tuning spark.task.pis for multi-threaded operations. These clusters provide better price performance for CPU-bound workloads compared to general-purpose instances. Storage optimized clusters for high throughput input-output utilize instances with local NVMe SSDs, like AWS i3 or Azure L Series, for workloads requiring fast local storage. They excel at shuffle-heavy operations like large joins and aggregations, iterative algorithms that repeatedly read intermediate data, and Delta Lake operations with frequent file rewrites. Configuration involves setting spark.local.dir to use local SSDs for shuffle data, tuning spark.shuffle.file.buffer and spark.reducer.maxblocks in flight per address for input-output optimization, enabling spark.sql.adaptive.colli skip partitions to reduce shuffle files, and configuring Delta Cache to use local SSDs effectively. These clusters significantly improve performance for input-output bound workloads, especially those with large shuffles. GPU accelerated clusters for deep learning and AI leveraged GPU instances, like AWS P3 or Azure North Carolina Series, for machine learning and deep learning workloads. They provide massive parallelization for matrix operations, neural network training, and inference at scale. Configuration requires selecting appropriate GPU types based on model requirements, V100 for training, T4 for inference, setting appropriate GPU memory allocation, configuring CUDA compatibility, and tuning batch sizes for optimal GPU utilization. These clusters integrate with frameworks like TensorFlow, PyTorch, and Rapids for GPU accelerated data processing. While expensive, they can be 10-100x faster than CPU clusters for appropriate workloads. Auto-scaling and spot instance strategies optimize costs while maintaining performance. Auto-scaling should be configured with appropriate thresholds, aggressive for development clusters, conservative for production streaming. Spot preemptible instances work well for fault-tolerant batch workloads, but should be avoided for streaming or time-sensitive jobs. Mixed instance types and pools provide flexibility and availability. The key is setting maximum nodes to prevent runaway costs, while ensuring minimum nodes meet baseline performance requirements. Cluster policies should enforce these configurations consistently across the organization. Documentation. Cluster configuration best practices emphasize the advantages of DLT for idle process in Databricks, Delta Live Tables, DLT, or Lakehouse Declarative Pipeline, LDP, revolutionizes idle development by providing a declarative framework that manages infrastructure, orchestration, and data quality automatically. Declarative pipeline development fundamentally changes how data engineers build pipelines. Instead of writing procedural code that describes how to process data, you declare what the final data set should look like, and DLT handles the execution details. This declarative approach means you define transformations as SQL or Python functions that describe the relationship between datasets, and DLT automatically determines the correct execution order based on dependencies. It manages incremental processing, determining which data needs to be reprocessed when sources change. The framework handles retries, error recovery, and state management automatically, eliminating boilerplate code that typically comprises 60-80% of traditional ETL pipelines. This approach reduces development time from weeks to days and makes pipelines more maintainable since the business logic is clearly separated from infrastructure concerns. Automatic data quality management embeds quality controls directly into pipeline definitions through expectations. Expectations are declarative data quality rules that can warn, drop, or fail records based on conditions you define. For example, you can specify that customer IDs must not be null, dates must be within reasonable ranges, or numerical values must fall within expected bounds. DLT automatically tracks quality metrics, showing how many records pass or fail each expectation over time. This visibility helps identify data quality trends and source system issues before they impact downstream analytics. The framework generates data quality dashboards automatically, providing observability without additional development effort. Quarantine patterns are easily implemented, where failed records are routed to separate tables for investigation rather than being lost. Built-in development and deployment best practices eliminates the need to build supporting infrastructure typically required for production pipelines. DLT provides automatic versioning of pipeline definitions and data, enabling easy rollback when issues occur. It includes built-in monitoring and alerting, notifying you when pipelines fail or when quality metrics exceed thresholds. The development lifecycle is streamlined with separate development and production modes, allowing you to test changes with sample data before deploying to production. Pipeline updates use a blue-green deployment pattern, ensuring zero downtime during updates. Change Data Capture (CDC) is natively supported, automatically handling insert, update, and delete operations from source systems. Performance optimization and cost management happen automatically without manual tuning. DLT automatically optimizes file sizes, implements Z-ordering on commonly filtered columns, and manages partition pruning to minimize data scanning. It scales compute resources based on workload demands, adding nodes during peak processing and removing them during idle periods. The framework implements intelligent caching, keeping frequently accessed data in memory across pipeline runs. Incremental processing ensures only changed data is processed, dramatically reducing compute costs compared to full reprocessing. Pipeline clustering allows multiple pipelines to share compute resources, improving utilization and reducing costs. The automatic optimization often results in 10x performance improvements compared to manually tuned pipelines. Documentation. Delta Live Tables Overview. Advantages of Delta Live Tables. Implement data pipelines using DLT. Implementing DLT pipelines requires understanding both the declarative syntax and the operational patterns that make pipelines maintainable and reliable. Creating DLT pipeline definitions starts with organizing your code into notebooks or Python files that define datasets. Each dataset is declared using decorators at dlt.table or at dlt.view in Python or create live table statements in SQL. A basic implementation might look like Python at dlt.table, comment equals, clean customer records, partition underscore cos equals, region, table underscore properties equals, quality, silver, at dlt.expect underscore or underscore drop, valid underscore email. Email is not null, at dlt.expect underscore or underscore drop, valid underscore age greater than equals 0 and age less than equals 120, def cleaned underscore customers. Return dlt.read raw underscore customers. Filter code is underscore deleted equals false. Select customer underscore id, email, age, region. This declaration defines data quality rules, partitioning strategy, and transformation logic in one place. Tables materialize results to storage, while views are computed on demand, allowing you to balance performance and storage costs. Managing dependencies and data flow happens automatically through dataset references. When one dataset references another using dlt.read or select from live syntax, DLT builds a dependency graph and executes transformations in the correct order. You can create multi-hop architectures, where bronze tables read from sources, silver tables read from bronze, and gold tables aggregate from silver. Circular dependencies are automatically detected and prevented. The framework supports fan-out patterns, where multiple downstream tables consume from one upstream table, and fan-in patterns where one table combines multiple sources. Conditional logic can be embedded using Python functions, allowing different transformation paths based on runtime parameters or data characteristics. Handling streaming and batch workloads is unified in DLT through consistent APIs. Streaming sources are declared using @dlt.table, table underscore properties equals, pipelines.reset.allowed, false, to prevent full refresh, while batch sources allow complete reprocessing. You can implement Lambda architectures where streaming provides low latency updates and batch ensures completeness. Python @dlt.table def orders. Streaming equals dlt.read underscore stream. Kafka underscore orders. With watermark, timestamp, 1 hour, batch equals dlt.read, database underscore orders. Filter, timestamp, less than current underscore timestamp. Expressway, interval 1 hour, return streaming.union, batch. The framework handles watermarking, state management, and exactly once processing automatically for streaming sources. Deployment and monitoring patterns ensure reliable production operations. Pipelines are deployed through the CLI or REST API with configuration that specifies target schemas, compute resources, and runtime parameters. Development pipelines can use sample datasets in smaller clusters, while production pipelines process complete data with auto-scaling clusters. Continuous pipelines run constantly for real-time processing, while triggered pipelines run on schedules or events. Pipeline events are logged to event tables, enabling custom monitoring and alerting. You can implement circuit breakers using expectations that fail pipelines when critical quality thresholds are exceeded. The Pipeline API allows programmatic management, enabling CI/CD integration where pipelines are tested and staging before production deployment. Documentation. LDP pipelines identify DDL, data definition language, /DML features. Understanding DDL and DML operations in Databricks is fundamental for managing data structures and manipulating data effectively within the platform. Table creation and schema management encompasses various approaches to defining data structures. Create table supports multiple patterns. Creating managed tables where Databricks controls both metadata and data files. External tables that reference existing data locations. And temporary views for session-specific transformations. Delta tables can be created with using Delta, specifying properties like partition by for partition columns, cluster by for Z ordering optimization, and table properties for metadata and configuration. Schema evolution is handled through alter table commands that can add columns with specified positions. After, first, alter column to change types or add comments, and drop columns when removing fields. Create table as select. This creates new tables from query results. while create or replace table provides idempotent table creation. Describe commands reveal table structure, partitioning, and properties, with describe extended showing additional metadata like location and format. Data modification operations provide comprehensive capabilities for managing data within tables. Insert operations support multiple patterns. Insert into for appending data. Insert overwrite for replacing data. Partition specific or entire table. And multi-row inserts using values or select statements. Update operations leverage Delta Lake's ASINT capabilities to modify existing records based on conditions, supporting complex expressions and subqueries. Delete operations remove records while maintaining transaction history, enabling time travel queries to see deleted data. Merge, upsert, operations provide powerful conditional logic for simultaneously handling inserts, updates, and deletes based on matching conditions. SQL merge into target using source on target.id equals source.id when matched, and source.is underscore deleted equals true then delete when matched then update set asterisk. When not matched then insert asterisk. This single operation replaces complex procedural logic typically required for slowly changing dimensions. Database and catalog management organizes tables into logical groupings. Create database, or schema, establishes namespaces for tables with optional location for managed table storage and comment for documentation. Use statements set default databases, eliminating the need for fully qualified table names. Show commands provide discovery capabilities. Show databases lists available schemas. Show tables reveals tables in a database. And show create table displays the DDL to recreate tables. With Unity Catalog, 3-level namespaces, catalog.database.table, provide additional organization and governance capabilities. Grant and revoke statements manage permissions at catalog, database, and table levels, implementing fine-grained access control. Advanced DDL features extend beyond basic table management. Generated columns compute values automatically based on other columns, useful for derived attributes that should be consistently calculated. Constraints like not null and check ensure data integrity at the table level. Table cloning creates deep or shallow copies for testing or backup purposes. Deep clone copies data and metadata, while shallow clone only copies metadata with references to original files. Vacuum removes old files no longer referenced by Delta tables, reclaiming storage space. Optimize reorganizes data files for better performance, with Zorter by co-locating related information. These maintenance operations are crucial for production table management. Documentation, DDL statements. DML statements compute complex aggregations and metrics with PySpark data frames. PySpark data frames provide powerful APIs for computing sophisticated aggregations and business metrics that go beyond simple summations and counts. Window functions for advanced analytics enable calculations across related rows without collapsing the dataset. Window specifications define partitions, grouping rows, and ordering for ranking and cumulative operations. Ranking functions like row underscore number, rank, and dense underscore rank identify top performers or create sequences within groups. For example, finding the top 3 products by revenue per category. Python from PySpark.sql import window from PySpark.sql.functions import asterisk window underscore spec equals window dot partition b category order b desk revenue df underscore ranked equals df dot with column rank dense underscore rank over window underscore spec filter cold rank less than equals 3 analytic functions like lead lag, and cumulative sums enable time series analysis, comparing current values to previous periods, or calculating running totals. Moving averages smooth out variations using window frames. rows between -6, 0 for 7-day moving averages. Percent rank and tile functions create percentile buckets for statistical analysis. Complex aggregation patterns combine multiple aggregation types in conditional logic. The ag function accepts multiple aggregation expressions, allowing computation of various metrics simultaneously. Python df.group b, region, product, ag, count, order underscore id, alias, order underscore count, sum, revenue, alias, total underscore revenue, ave, quantity, alias, ave underscore quantity, def, price, alias, price underscore variance, collect underscore set, customer underscore id, alias, unique underscore customers, percentile underscore approx, delivery underscore days, 0.5, alias, median underscore delivery, conditional aggregations using when, compute metrics for subsets, sum, when, status, equals return, amount, for return rates, grouping sets, roll up, and cube operations generate multiple aggregation levels in single queries, essential for OLAP style analysis. Pivot operations transform row values into columns, creating cross-stab reports for comparative analysis. User-defined aggregate functions, ADAFs, extend PySpark's aggregation capabilities for custom business logic. While Python ADAFs have performance implications, they enable complex calculations not possible with built-in functions. Pandas UDFs provide better performance for grouped operations. Python at pandas underscore UDF, return type equals, double, function type equals pandas UDF type dot grouped underscore ag, def weighted underscore ave, values, weights, return, values asterisk weights, sum, slash weights dot sum, df dot group b, category, ag, weighted underscore ave, price, quantity. These functions can implement custom statistical measures, complex business rules, or domain-specific calculations that would be difficult to express in SQL. Performance optimization for aggregations ensures complex calculations complete efficiently. Broadcast joins for dimension tables eliminate shuffles when joining aggregated results with reference data. Salting techniques distribute skewed aggregation keys across multiple partitions, preventing hotspots. Pre-aggregating data at multiple granularities, hourly, daily, monthly, accelerates dashboard queries. Approximate algorithms like approx underscore count underscore distinct and percentile underscore approx trade accuracy for speed when exact values aren't required. Caching intermediate results prevents recomputation and iterative analysis. Adaptive query execution automatically optimizes aggregation strategies based on data statistics, coalescing partitions, and choosing appropriate join strategies. Documentation. PySpark data frame operations section 4. Productionizing data pipelines identify the difference between DAB and traditional deployment methods. The Databricks asset bundles. DAB represents a paradigm shift in how data assets are packaged, versioned, and deployed compared to traditional notebook-centric approaches. Traditional deployment challenges highlight why a new approach was needed. Traditional methods typically involve manually copying notebooks between environments, leading to configuration drift and deployment errors. Each notebook contains its own configuration, making it difficult to maintain consistency across development, staging, and production environments. Dependencies between notebooks are implicit, requiring careful documentation and manual orchestration. Version control is limited to individual notebooks, making it challenging to deploy related changes atomically. Environment-specific settings like cluster configurations, secrets, and connection strings are often hard-coded or managed through separate configuration notebooks, Rollbacks require manually reverting individual notebooks and hoping dependencies remain compatible. These challenges multiply as teams grow and pipelines become more complex. DAB's bundle-based approach treats related assets as a cohesive unit that can be developed, tested, and deployed together. A bundle includes all notebooks, libraries, configurations, and job definitions required for a complete solution. Configuration is externalized into YAML files that define environment-specific settings, enabling the same code to run across multiple environments with different configurations. Dependencies are explicitly declared, ensuring correct deployment order and preventing broken references. Version control operates at the bundle level, allowing atomic deployments and easy rollbacks of entire solutions. The bundle structure enforces best practices like separating code from configuration and organizing assets logically. Development workflow improvements streamline the entire lifecycle from development to production. Local development using the Databricks CLI or Versus code extensions provides a familiar IDE experience with syntax highlighting, auto-completion, and integrated debugging. Bundles can be validated locally before deployment, catching configuration errors early. Continuous integration pipelines can automatically test bundles using different configurations, ensuring changes work across all target environments. Deployment becomes a single command that updates all related assets atomically, eliminating partial deployments that leave systems in inconsistent states. The ability to parameterize bundles enables deployment time customization without code changes. Operational benefits extend beyond deployment to ongoing maintenance and governance. Bundles provide a clear inventory of all assets related to a solution, simplifying documentation and knowledge transfer. Dependency tracking ensures that changes to shared libraries or tables trigger appropriate downstream updates. Environment promotion follows a clear path from development to production with automated validation at each stage. Rollback capabilities allow quick recovery from failed deployments by reverting to previous bundle versions. Audit trails show who deployed what and when, supporting compliance and troubleshooting requirements. The standardized structure makes it easier for teams to understand and maintain each other's code. Documentation. Databricks asset bundles identify the structure of asset bundles. Understanding the structure of asset bundles is essential for organizing and deploying complex data solutions effectively. Bundle configuration file, Databricks.yml, serves as the manifest that defines the bundle structure and deployment behavior. This YAML file contains the bundle metadata including name, version, and description. It defines variables that can be referenced throughout the bundle, enabling parameterization of cluster sizes, data paths, and other settings. Environment configurations specify different targets, development, staging, production, with environment-specific overrides for variables, permissions, and compute resources. Resource definitions list all jobs, pipelines, and models included in the bundle with their configurations. Dependencies on libraries, both workspace libraries and external packages, are declared centrally. The configuration file supports interpolation, allowing values to reference other variables and environment variables, reducing duplication and ensuring consistency. Source code organization follows a logical structure that separates concerns and promotes reusability. The src/directory contains the main code assets including Python modules, SQL files, and notebooks. Libraries and utility functions reside in separate modules that can be imported across notebooks and jobs. Configuration files for specific components, like Delta Live tables pipeline definitions, are organized by function. The test/directory houses unit tests and integration tests that validate bundle functionality. Requirements files specify Python package dependencies with version constraints. The category file ensures that generated files and local configurations aren't committed to version control. This structure promotes code reuse and makes it easy to understand the bundle's components. Resource definitions specify the computational assets that process data. Job definitions include workflow specifications with tasks, dependencies, and scheduling information. Each job can reference notebooks or Python files within the bundle, specify cluster configurations, and define parameters. Delta Live tables pipelines are defined with their source notebooks, target schemas, and processing modes. ML models include training code, model artifacts, and serving configurations. Cluster policies ensure consistent compute configurations across deployments. Alert definitions specify monitoring conditions and notification channels. These resources reference code within the bundle using relative paths, maintaining portability across environments. Deployment artifacts and metadata support the bundle lifecycle. The Databricks/directory contains generated files and deployment state, which should not be committed to version control. Log files capture exact dependency versions for reproducible deployments. Deployment history tracks what was deployed when and by whom. Validation reports from pre-deployment checks ensure bundles meet quality standards. Documentation files explain the bundle's purpose, setup instructions, and operational procedures. CI/CD configuration files, like GitHub workflows or Azure-pipelines.yml, automate testing and deployment. These artifacts ensure bundles can be reliably deployed and maintained over time. Documentation. Bundle structure: deploy a workflow, repair, and rerun a task in case of failure. Managing workflow failures effectively requires understanding the various recovery mechanisms and when to apply each approach. Workflow deployment strategies establish the foundation for reliable pipeline operations. Workflows should be deployed with comprehensive error handling, including retry configurations at both the job and task levels. Task dependencies must be carefully defined to ensure proper execution order and enable partial reruns. Timeout settings prevent runaway jobs from consuming resources indefinitely. Notification configurations alert appropriate teams when failures occur. Using job clusters instead of all-purpose clusters ensures clean execution environments and cost optimization. Parameterized workflows enable flexibility without code changes, supporting different data ranges or processing modes. Version control integration ensures that the exact code version can be identified and reproduced for any job run. Failure detection and root cause analysis begins immediately when a task fails. The job run history provides detailed information about what succeeded and what failed, including error messages, logs, and execution metrics. Task level logs reveal specific errors, whether they're data related, null values, type mismatches, infrastructure related, cluster failures, network issues, or code related, syntax errors, logic bugs. The Spark IE shows detailed execution plans, helping identify performance issues that might cause timeouts. Ganglia metrics reveal resource constraints like memory pressure or disk space issues. Structured streaming checkpoints indicate where streaming jobs failed and what data remains unprocessed. Understanding the failure type determines the appropriate recovery strategy. Repair runs for partial recovery enable efficient recovery without reprocessing successful tasks. When initiating a repair run, Databricks automatically identifies failed and downstream tasks that need to be rerun. You can optionally include upstream tasks if the failure might be due to incomplete or incorrect upstream processing. Repair runs maintain the same job run ID, preserving the execution context and making it easier to track the complete job history. Parameters from the original run are preserved unless explicitly overridden. For workflows with multiple parallel branches, repair runs only reprocess the affected branch, saving time and compute resources. The repair run inherits the cluster configuration from the original run but starts fresh clusters, eliminating any corrupted state. Rerun strategies and best practices address different failure scenarios. Complete reruns are appropriate when data quality issues affect the entire pipeline, or when significant code changes require full reprocessing. Selective reruns using date parameters allow reprocessing specific time periods without affecting other data. For streaming jobs, checkpoint management determines whether to resume from the last successful batch or start fresh. Idempotent job design ensures that reruns produce consistent results without creating duplicates or data corruption. Implementing circuit breakers prevents continuous failures from consuming resources when underlying issues aren't resolved. Creating separate recovery workflows for common failure scenarios streamlines the recovery process. Regular failure drills ensure teams know how to respond when production issues occur. Documentation. Managing job runs use serverless for a hands-off. Auto-optimized compute managed by Databricks serverless compute eliminates infrastructure management overhead while providing optimal performance through automatic optimization and scaling. Serverless architecture benefits transform how teams interact with compute resources. With serverless, there's no cluster startup time. Compute is instantly available when needed. Resources automatically scale based on workload demands, from zero during idle periods to thousands of cores during peak processing. Databricks manages all infrastructure updates, security patches, and runtime optimizations transparently. Cost allocation is granular, charging only for actual compute time used rather than cluster uptime. Multi-tenancy optimizations allow Databricks to achieve better resource utilization, passing savings to customers. The elimination of cluster management reduces operational overhead and allows teams to focus entirely on data and analytics rather than infrastructure. Also, cost efficiency. You are billed only for the time the compute is actively running your workload, and the platform automatically optimizes resource utilization to reduce costs. Automatic performance optimization happens continuously without user intervention. Databricks automatically selects appropriate instance types based on workload characteristics. File formats are optimized transparently, with automatic compression and encoding selection. Query plans are dynamically optimized using the latest statistics and runtime feedback. Caching strategies adapt based on access patterns, keeping frequently used data in memory. Data layout is continuously optimized through background compaction and reorganization. Photon acceleration is automatically applied where beneficial. These optimizations often result in 2-3x performance improvements compared to manually tuned clusters, while requiring zero configuration effort. Serverless SQL warehouses provide instant SQL analytics capabilities. Queries start executing immediately without waiting for infrastructure provisioning. Intelligent caching across queries means common data sets remain in memory, dramatically improving response times for dashboards and reports. Automatic scaling handles concurrent users gracefully, adding compute resources as query load increases. Query routing ensures small queries don't get stuck behind large analytical workloads. Predictive scaling anticipates load patterns, pre-warming resources before peak times. The serverless architecture enables features like query result caching across users, improving performance for shared dashboards and reports. Serverless workflows and notebooks extend the serverless paradigm to all workload types. Notebook execution on serverless compute eliminates the need to manage interactive clusters. Workflows can mix serverless and dedicated compute, using serverless for variable workloads and dedicated clusters for predictable, High volume processing. Development environments benefit from instant startup and automatic shutdown, reducing costs for intermittent usage. Testing and CI/CD pipelines run faster with immediate compute availability. Serverless compute handles burst workloads efficiently, automatically scaling to meet demand without over-provisioning. The pay-per-use model makes it cost-effective for sporadic or unpredictable workloads, where maintaining dedicated clusters would be wasteful. Documentation. Serverless compute analyzing the Spark AI to optimize the query. The Spark AI provides essential insights for understanding query performance and identifying optimization opportunities that can dramatically improve execution times. Understanding the jobs and stages view reveals the high-level structure of query execution. Each action in your code triggers a job, which is divided into stages based on shuffle boundaries. The job timeline shows parallelism and identifies stragglers, tasks that take significantly longer than others. Stage details reveal the number of tasks, data volumes processed, and shuffle characteristics. Look for stages with many tasks but little data, indicating over-partitioning, or few tasks with large data volumes, suggesting under-partitioning. Skip stages indicate successful caching, while repeated stages suggest missing cache opportunities. The DAG visualization shows data flow and helps identify unnecessary shuffles or redundant computations. Understanding these patterns helps restructure queries for better performance. Analyzing task-level metrics uncovers performance bottlenecks at the execution level. Task duration distribution reveals data skew, when a few tasks take much longer than others. Shuffle read-write metrics indicate data movement overhead, with high shuffle volumes suggesting the need for broadcast joins or better partitioning strategies. Spill metrics, memory and disk, indicate memory pressure, suggesting the need for more memory or better data organization. GC time reveals memory management overhead, with high GC indicating the need for memory tuning. Input-output metrics show data scanning efficiency, with high input relative to output suggesting the need for better predicate pushdown or partitioning. Failed tasks and their error messages reveal data quality issues or resource constraints. SQL tab for query plan analysis provides deep insights into data frame and SQL query execution. The parse logical plan shows what Spark understood from your query, helping identify if the query structure matches intentions. The analyze logical plan includes resolve column references and data types, revealing type mismatches or unnecessary casts. The optimize logical plan shows catalyst optimizer transformations, including predicate pushdown, constant folding, and join reordering. The physical plan details the actual execution strategy, including join types, broadcast, sort merge, shuffle hash, aggregation strategies, hash, sort, and exchange, shuffle operations. Comparing plans between fast and slow queries reveals optimization opportunities like missing broadcasts or inefficient join orders. Storage and executor metrics help identify resource constraints and inefficiencies. The Storage tab shows cached RDDS and data frames with their memory disk usage and fraction cached. Low cache utilization suggests overcaching, while cache eviction indicates insufficient memory. The Executors tab displays resource usage across nodes, including memory usage, storage versus execution, task execution metrics, and data locality statistics. Imbalanced executor metrics indicate data skew or inefficient partitioning. High disk spill on specific executors reveals hot partitions. Network input-output patterns show if data transfer is a bottleneck. These metrics guide decisions about cluster sizing, partitioning strategies, and caching policies. Documentation. Spark AI Guide Section 5. Data governance and quality explain the difference between managed and external tables. Understanding the distinction between managed and external tables is fundamental for designing data architectures that balance control, performance, and governance requirements. Managed tables. Full lifecycle control means Databricks controls both the method data and the underlying data files. When you create a managed table, Databricks stores the data in a default location within the workspace's managed storage. Dropping a managed table deletes both the method data from the metastore and the actual data files from storage, ensuring clean cleanup. Managed tables benefit from automatic optimization features like auto compaction and optimized writes without additional configuration. They integrate seamlessly with Unity Catalog, inheriting governance policies and access controls automatically. Performance optimizations like caching and indexing are handled transparently. Managed tables are ideal for derived datasets, intermediate transformations, and any data where Databricks should handle the complete lifecycle. They simplify operations, since you don't need to manage file locations or worry about orphan data. External tables. Flexible data management reference data stored in locations you specify and control. The metadata is registered in the metastore, but the data remains in your designated storage location. Dropping an external table only removes the metadata. The underlying data files remain untouched. This separation is crucial when multiple systems need to access the same data, when you need to maintain specific storage layouts for compliance, or when migrating existing data lakes to Databricks. External tables support various formats: Parquet, Bork, Avro, Sin, CSV, and can reference data in cloud storage, S3, ATOS, GCS, or on-premises systems through Lakehouse Federation. You maintain full control over data organization, including partitioning schemes and file layouts. However, you're responsible for data maintenance tasks like compaction and cleanup. Governance and security implications differ significantly between table types. Managed tables in Unity Catalog automatically inherit catalog and schema level permissions, simplifying security management. Data access is controlled entirely through Databricks, providing consistent audit trails. External tables require careful permission management both in Databricks and at the storage level, ensuring that direct file access doesn't bypass security controls. With external tables, you must ensure that storage level permissions align with Databricks permissions to prevent unauthorized access. Managed tables provide better data lineage tracking since all operations go through Databricks. External tables may have gaps in lineage if data is modified outside Databricks. Performance and optimization considerations influence table type selection. Managed tables automatically benefit from Delta Lake optimizations including file compaction, Z-ordering, and data skipping. Query performance is generally better with managed tables due to these automatic optimizations. External tables require manual optimization efforts, but offer more control over physical data layout. For frequently queried data, managed tables provide better out-of-box performance. External tables are advantageous when you need specific physical layouts for compatibility with other systems, or when data volumes are so large that storage location flexibility is crucial. The choice often involves balancing automation benefits against control requirements. Documentation. Managed versus external tables identify the grant of permissions to users and groups within UC. Unity Catalog provides a comprehensive security model that enables fine-grained access control across all data assets in your lakehouse. Hierarchical permission model establishes inheritance and precedence rules for access control. Permissions flow from catalogs to schemas to tables, with grants at higher levels automatically applying to child objects. The use permission enables browsing and discovery, allowing users to see what objects exist. Select permission allows reading data from tables and views. Modify permission enables insert, update, and delete operations. Create permission allows creating new objects within a container, tables in a schema, schemas in a catalog. Owner privileges provide full control, including the ability to grant permissions to others. Permissions are additive. Users get the union of all permissions granted directly and through group membership. Deny permissions aren't supported. Security is managed through explicit grants only. This model simplifies administration while providing precise control over data access. Granting and managing permissions follows SQL standard syntax with the Databricks extensions. Basic grants use the pattern grant privilege on object to principal. For example, grant select on table catalog.schema.table to user at company.com provides read access to a specific table. Multiple privileges can be granted in one statement. Grant select. Modify on schema catalog.schema to analyst_group. The with grant option allows recipients to grant the same permissions to others, enabling delegated administration. Revoke statements remove permissions, with cascade option revoking dependent grants. Show grants displays current permissions for objects or principals, essential for auditing access. All privileges shortcuts grant all applicable permissions for an object type. Group-based access management simplifies administration for large organizations. Groups can be synchronized from identity providers, Azure AD, Okta, ADFS, or created locally in Databricks. Nested groups are supported, enabling hierarchical organization structures. Best practices include creating functional groups, data_engineers, data_scientists, analysts, rather than per project groups, using naming conventions that indicate purpose and scope, and regularly reviewing group membership for accuracy. Dynamic groups based on attributes enable automatic membership management. Service principals represent applications and automated processes, enabling secure programmatic access. Groups should align with data classification levels, ensuring users only access data appropriate to their clearance level. Advanced permission patterns address complex security requirements. Row-level security uses views with filters based on user context. Create view filtered _cells as select asterisk from cells, where region equals current _user. Column level security masks sensitive fields using views or column masks. Dynamic views change their output based on the accessing user's permissions, enabling single views that show different data to different users. Secure functions encapsulate complex authorization logic that can be reused across views. Permission boundaries prevent privilege escalation by limiting what owners can grant. Audit-safe views ensure that permission checks happen at query time, not view creation time. These patterns enable sophisticated security models while maintaining query performance. Documentation. Unity Catalog privileges identify key roles in UC. Unity Catalog defines specific roles that work together to provide comprehensive governance while enabling self-service analytics. Account admins. Platform governance hold the highest level of administrative control across the entire Databricks account. They manage Unity Catalog metastores, including creation, configuration, and assignment to workspaces. Account admins control identity federation, configuring how users and groups synchronize from corporate identity providers. They establish account-level policies for compute, clusters, and storage that apply across all workspaces. Billing and usage monitoring falls under their purview, enabling cost control and chargeback. They delegate workspace-level administration by assigning workspace admins. Account admins also manage the data sharing agreements and external connections that span organizational boundaries. This role typically belongs to IT administrators or cloud platform teams who ensure the Databricks platform aligns with organizational standards. Metastore admins. Data platform management manage the Unity Catalog Metastore and its global policies. They create and manage catalogs, the top-level containers for data assets. Storage credentials and external locations are configured by Metastore admins, controlling where data can be stored. They establish naming conventions and organizational standards for catalogs and schemas. Metastore admins manage the system tables that track usage, lineage, and audit logs. They configure Metastore level settings like default catalog and automatic maintenance jobs. This role bridges the gap between platform administration and data governance, often held by data platform teams or senior data engineers. Metastore admins ensure consistent governance across all workspaces attached to the Metastore. Catalog owners. Domain data governance manage specific catalogs and all objects within them. They create and organize schemas to support their domain's analytical needs. Catalog owners grant permissions to users and groups who need access to their domain's data. They establish and enforce data quality standards for their catalog. Schema creation and table management fall under their control. They coordinate with data engineers to ensure proper data ingestion and transformation. Catalog owners often represent business domains or data products, taking responsibility for data quality, documentation, and access management within their domain. This role enables decentralized governance while maintaining central oversight. Data owners and stewards. Asset level responsibility manage individual tables, views, and schemas. They understand the business context and meaning of the data they own. Data owners grant appropriate access permissions based on business requirements and compliance needs. They ensure data documentation is accurate and current, including descriptions, tags, and business metadata. They monitor data quality metrics and address issues as they arise. Data stewards work with data owners to implement governance policies, often handling day-to-day permission requests and quality monitoring. These roles are typically held by business analysts or subject matter experts who understand both the data and its business context. Documentation. Admin privileges in Unity Catalog identify how audit logs are stored. Audit logging in Unity Catalog provides comprehensive tracking of all activities, essential for security, compliance, and operational monitoring. System tables for audit storage centralize all audit information and queryable Delta tables within Unity Catalog. The audit logs are stored in the system catalog, accessible through tables like system.access.audit. These tables are automatically maintained by Databricks, with new events continuously appended. The Delta format ensures asset compliance and enables time travel queries to investigate historical events. Partitioning by date optimizes query performance for time range searches. Retention policies automatically manage storage, typically keeping 90 days of detail logs with longer retention for aggregated data. The structured format enables standard SQL queries for analysis, making audit investigation accessible to analysts without specialized tools. Audit event categories and schema organize different types of activities for easier analysis. Data access events track every query, including who accessed what data, when, and from where. DDL/DML events record all schema changes and data modifications with before-after states. Permission changes log all grant and revoke operations with full details of privileges affected. Authentication and session events track user logins, API access, and session duration. Compute events record cluster creation, termination, and configuration changes. Each event includes standard fields like user identity, timestamp, IP address, workspace ID, and request ID for correlation. Additional fields vary by event type, providing context-specific information like query text, affected objects, or error details. Querying and analyzing audit logs enables various compliance and security use cases. Common query patterns include finding all users who access specific sensitive tables, identifying permission changes for compliance reporting, detecting unusual access patterns that might indicate security threats, and calculating usage metrics for chargeback or optimization. Views can be created to simplify common audit queries and mask sensitive information for broader access. Time-based analysis reveals access patterns and helps identify anomalies. Joining audit logs with data lineage provides end-to-end visibility of data flow. Integration with external SIEM tools happens through scheduled exports or streaming queries, enabling centralized security monitoring. Compliance and retention management ensures audit logs meet regulatory requirements. Immutable storage prevents tampering with audit records, crucial for compliance. Access to audit logs is restricted through Unity Catalog permissions, ensuring only authorized personnel can view sensitive activity data. Export capabilities enable archival to external systems for long-term retention beyond built-in limits. Automated reports can be generated for compliance officers, showing access to regulated data. Data residency requirements are met by storing audit logs in the same region as the data. Regular validation ensures audit logging remains complete and accurate. Integration with organizational compliance tools provides consolidated reporting across multiple systems. Documentation. Audit logging use lineage features in Unity Catalog. Data lineage in Unity Catalog provides visual and programmatic tracking of how data flows through your lakehouse, essential for impact analysis and regulatory compliance. Automatic lineage capture tracks data dependencies without manual documentation. Every query execution automatically records which tables were read and written, building a comprehensive dependency graph. Column-level lineage tracks how individual fields flow and transform through pipelines. Notebook and job executions contribute to lineage, showing which code processes which data. Delta Live tables pipelines provide especially rich lineage, capturing the complete transformation logic. External data sources are included when accessed through Lakehouse Federation. The lineage system handles complex scenarios including views, CTES, and nested queries. Updates occur in near real time, ensuring lineage information is current. No code changes are required. Lineage capture happens transparently for all Unity Catalog operations. Lineage visualization and navigation makes complex data relationships understandable. The lineage graph shows upstream sources and downstream consumers for any table or column. Interactive exploration allows drilling into specific transformation steps or expanding to see broader context. Time-based views show how lineage evolved, crucial for understanding historical data flows. Filtering capabilities focus on specific schemas, time periods, or transformation types. Impact analysis reveals what breaks if a table changes, essential for change management. Root cause analysis traces data quality issues back to their source. The visual interface supports both technical and business users, with appropriate detail levels for each audience. Export capabilities enable sharing lineage diagrams and documentation or presentations. Programmatic lineage access enables automated governance and analysis workflows. REST APIs provide programmatic access to lineage data for integration with external tools. System tables store lineage information in queryable format, enabling SQL-based analysis. Common queries include finding all tables dependent on a specific source, identifying unused tables with no downstream consumers, and calculating the freshness of derived tables based on source update times. Lineage data can trigger automated workflows, like refreshing downstream tables when sources update. Integration with data quality tools enables automatic quality check propagation through lineage chains. Custom applications can leverage lineage for automated documentation generation or compliance reporting. Lineage for compliance and governance addresses regulatory requirements for data traceability. GDPR compliance uses lineage to track personal data propagation for erasure requests. Financial regulations require demonstrating data accuracy through transformation documentation. Lineage provides evidence for audit trails, showing how reported numbers were calculated. Change management processes use lineage for impact assessment before modifications. Data classification propagates through lineage, ensuring derived data inherits appropriate security levels. Retention policies consider lineage dependencies, preventing premature deletion of required source data. Regular lineage validation ensures completeness and accuracy for compliance reliance. Documentation. Data lineage use the delta sharing feature available with Unity Catalog to share data. Delta sharing enables secure data sharing across organizations without data copying, maintaining governance and access control. Creating and managing shares establishes the foundation for data collaboration. Shares are containers that group tables for external access. Creating a share involves selecting tables from Unity Catalog and defining what data is exposed. Views can filter or aggregate data, sharing derived insights rather than raw data. Partition filtering limits shared data to specific time ranges or regions. Column masking hides sensitive fields while sharing useful analytics. Share configuration includes metadata like description and contact information for data consumers. Versioning allows updating shared data structures while maintaining backward compatibility. Multiple shares can expose different views of the same underlying data for different audiences. Recipient management and access control ensure secure data distribution. Recipients are external entities authorized to access shares. Each recipient receives unique credentials that authenticate their access. Token-based authentication provides secure, rotatable access without password sharing. IP whitelisting restricts access to approved networks. Time-based access enables temporary sharing for specific projects. Usage tracking monitors what data recipients actually access. Revocation immediately terminates access without affecting other recipients. Audit logs capture all sharing activities for compliance. Recipients can be organizations using Databricks or any platform supporting Delta sharing protocol. That is, Delta sharing supports two types of recipients: Databricks to Databricks. This is a seamless way to share data with users in another Databricks workspace. No tokens are required. The data becomes available as soon as access is granted. Open sharing. This allows you to share data with non-Databricks users or external systems using a secure activation link to download token-based credentials. Consuming shared data provides seamless integration for data recipients. Databricks recipients see share tables appear like regular Unity Catalog tables. SQL queries work normally, with query optimization happening on the provider side. Power BI, Tableau, and other BI tools connect directly using Delta sharing connectors. Python and Pandas integration enables data science workflows without infrastructure setup. Spark applications read shared data using the Delta sharing library. Real-time updates ensure recipients always see current data without synchronization. Schema evolution is handled gracefully, with recipients seeing new columns as they're added. Performance optimizations like column pruning and predicate pushdown work across organizational boundaries. Governance and compliance considerations ensure sharing meets regulatory requirements. Data never leaves the provider's environment. Only authorized queries are executed. Fine-grained access controls determine exactly what each recipient can see. Audit trails track all access for compliance reporting. Data residency requirements are met since data doesn't physically move. Encryption in transit protects data during query execution. Cost allocation tracks compute resources used by recipients. Change management processes ensure sharing agreements remain current. Legal agreements can be enforced through technical controls. Regular reviews ensure shared data remains appropriate and access is still needed. Documentation. Delta sharing identify the advantages and limitations of delta sharing. Understanding both the benefits and constraints of delta sharing helps organizations make informed decisions about data collaboration strategies. Key advantages of delta sharing make it compelling for modern data collaboration. Zero data movement eliminates the costs, delays, and synchronization issues of traditional data sharing. Recipients always access live data, ensuring analytics are based on current information. The open protocol works across clouds and platforms, avoiding vendor lock-in. Centralized governance maintains control over shared data with consistent security policies. Fine-grained access control enables sharing specific rows and columns without exposing entire datasets. Built-in auditing provides complete visibility into how shared data is used. Performance optimizations like predicate pushdown and column pruning work seamlessly across organizations. Cost efficiency comes from eliminating data duplication and transfer charges. Schema evolution support means data structures can evolve without breaking recipient applications. Technical limitations to consider influence sharing architecture decisions. Read-only access means recipients cannot modify shared data, limiting collaborative workflows. No real-time streaming support currently exists. Sharing works with batch data only. Query performance depends on the provider's infrastructure and optimization. Complex joins between shared and local data may not optimize well. Some advanced Delta features like Z-ordering benefits may not transfer to recipients. Large result sets still require data transfer, potentially impacting performance. Change data capture, CDC, feeds aren't directly shareable, limiting incremental processing options. Time travel queries are restricted to versions the provider explicitly shares. Recipients cannot create indexes or materialize views on shared data. Also, egress costs. While Delta sharing within a single region incurs no egress costs, sharing data across different clouds or regions may incur data egress fees from your cloud vendor. Organizational and governance constraints affect sharing program success. Legal agreements must be established before technical sharing can begin. Data classification policies may prohibit sharing certain sensitive information. Cost allocation becomes complex when providers serve many recipients. Support responsibilities between provider and recipient need clear definition. Version management requires coordination when schema changes are needed. Quality SLAs are difficult to enforce across organizational boundaries. Different compliance requirements between organizations may limit sharing scope. Technical expertise is required on both sides for effective implementation. Cultural resistance to external data sharing may require change management. Best practices for maximizing value help organizations overcome limitations while leveraging advantages. Start with non-sensitive, high-value data sets to build confidence. Implement views that pre-aggregate or filter data for better performance. Use partition elimination to share only relevant data subsets. Establish clear SLAs for data freshness and availability. Monitor usage patterns to optimize shared data structures. Regular reviews ensure sharing agreements remain mutually beneficial. Automated testing validates that shared data meets quality standards. Documentation helps recipients understand and effectively use shared data. Cost models should fairly allocate infrastructure costs between parties. Governance committees should oversee sharing programs for strategic alignment. Documentation. Delta sharing. Identify types of delta sharing. Databricks versus external system. Delta sharing supports different integration patterns depending on whether recipients use Databricks or other platforms. Databricks to Databricks sharing provides the most seamless integration experience. Share tables appear directly in the recipient's Unity catalog with full SQL access. Query optimization happens automatically, with the provider's cluster handling computation. Column statistics and data skipping work transparently across organizations. Recipients can create views and derive tables based on shared data. Flow models can reference share feature tables directly. Delta Live tables pipelines can consume share tables as sources. Notebooks and jobs work with shared data without special configuration. All Databricks performance optimizations apply, including photon acceleration. The experience is essentially identical to working with local tables, abstracting away the complexity of cross-organization data access. Open sharing to external systems extends data access beyond the Databricks ecosystem. The Delta sharing protocol is open source, enabling any system to implement support. Apache Spark applications use the Delta sharing connector to read shared data directly. Python applications leverage the Delta sharing library for pandas data frames. Power BI and Tableau connect through native Delta sharing connectors for direct query. Java and Scala applications integrate using the Delta sharing client libraries. REST APIs enable custom applications to discover and access shared data. The protocol handles authentication, authorization, and data transfer efficiently. Performance optimizations like partition pruning work across different platforms. Schema metadata is shared in standard formats for broad compatibility. Protocol and connector differences impact integration approaches. Databricks to Databricks sharing uses optimized internal protocols for better performance. External sharing follows the Open Delta sharing protocol specification for compatibility. Native Databricks features like Unity Catalog governance apply only within Databricks. External systems may not support all Delta Lake features like Z-ordering benefits. Query pushdown capabilities vary based on the recipient platform sophistication. Streaming support differs, with some platforms limited to batch access. Error handling and retry logic may need custom implementation for external systems. Monitoring and debugging tools vary in capability across platforms. Implementation considerations by platform type guide architecture decisions. For Databricks recipients, focus on governance and cost allocation rather than technical integration. External SQL engines benefit from pre-aggregated views to minimize data transfer. Data science platforms should consider memory limitations when accessing large datasets. BI tools may require specific data modeling to optimize query performance. Streaming platforms might need intermediate staging for near real-time processing. Consider creating platform-specific shares optimized for each recipient type. Documentation requirements vary based on the recipient's technical sophistication. Support models should account for different platform capabilities and limitations. Documentation. Delta sharing analyzed the cost considerations of data sharing across clouds. Cross-cloud data sharing introduces complex cost dynamics that require careful analysis and optimization to remain economically viable. Data transfer and egress costs represent the most significant expense in cross-cloud sharing. Cloud providers charge substantial fees for data leaving their networks, egress, typically 8 cents-0.12 per gigabytes. These costs multiply quickly with frequent queries or large result sets. Ingress, data entering, is usually free, creating asymmetric cost models. Transfer costs vary by region, with intercontinental transfers costing more. Volume discounts may apply for consistent high-volume transfers, but require commitment. Network acceleration services improve performance but add costs. Understanding query patterns helps predict and optimize transfer costs. Caching strategies on the recipient side can reduce repeated transfers. Compression reduces transfer volume, but adds compute overhead. Same cloud, same region. Sharing data within the same cloud provider and region generally incurs no additional egress costs. Compute and processing costs accumulate on the provider side for query execution. The provider bears compute costs for all recipient queries against shared data. Complex queries consume more resources, increasing provider costs. Concurrent queries from multiple recipients require scaling compute resources. Photon acceleration improves performance but increases compute costs. Auto-scaling clusters provide flexibility, but may lead to unpredictable costs. Reserved instances or savings plans can reduce compute costs for predictable workloads. Query optimization directly impacts compute costs for both provider and recipient. Monitoring compute usage by recipient enables accurate cost allocation. Setting query limits or quotas prevents runaway costs from inefficient queries. Storage and optimization costs affect the total cost of ownership for shared data. Maintaining optimized data for sharing requires additional storage for indexes and caches. Z-ordering and compaction improve query performance, but need compute resources. Multiple versions for time travel increase storage requirements. Archival strategies balance accessibility with storage costs. Hot, warm, cold storage tiers optimize costs based on access patterns. Partition maintenance ensures efficient querying, but requires ongoing management. Metadata storage for governance and lineage adds incremental costs. Backup and disaster recovery for shared data doubles storage requirements. Regional replicas for performance may be necessary, but multiply storage costs. Cost optimization strategies help maintain economically sustainable sharing programs. Implement query result caching to avoid repeated expensive computations. Use partition elimination to minimize data scanning and transfer. Create aggregated views for common query patterns, reducing compute and transfer. Schedule batch transfers during off-peak hours for better rates. Negotiate enterprise agreements with cloud providers for volume discounts. Implement chargeback models that fairly allocate costs to recipients. Monitor and alert on unusual cost patterns to prevent bill shock. Regular cost reviews identify optimization opportunities and eliminate waste. Consider data locality by sharing from regions close to recipients. Evaluate hybrid approaches, where some data is replicated for frequent access. Documentation. Cloud pricing calculators identify use cases of Lakehouse Federation when connected to external sources. Lakehouse Federation enables querying external databases without moving data, essential for hybrid architectures and gradual cloud migrations. Operational analytics across systems enables real-time insights without data movement. Federation allows joining transactional data in PostgreSQL with analytical data in the Lakehouse for complete business views. Real-time dashboards can query operational databases directly, ensuring current information. Customer 360 views combine data from CRM systems, support databases, and data warehouses without complex setup. Financial reconciliation compares source system records with Lakehouse aggregates in real time. Inventory analytics join ERP systems with supply chain data for accurate stock levels. Federation eliminates the latency of batch huddle for time-sensitive analytics. Query pushdown ensures efficient execution by processing filters and aggregations at the source. This approach maintains single sources of truth while enabling integrated analytics. Hybrid cloud and migration scenarios support gradual transitions to cloud-based architectures. Organizations can query on-premises databases while incrementally moving workloads to the cloud. Legacy systems remain accessible during multi-year migration programs without disruption. Hybrid analytics span both cloud and on-premises data without choosing one location. Compliance requirements keeping certain data on premises don't prevent cloud analytics. Federation provides a migration testing ground, comparing results between systems. Gradual offloading moves historical data to the lakehouse, while keeping current data in source systems. This approach reduces migration risk and allows rollback if issues arise. Teams can adopt cloud analytics without waiting for complete data migration. Multi-database integration patterns simplify complex data landscapes. Federation creates virtual data warehouses spanning multiple database technologies. MySQL, PostgreSQL, SQL Server, and Oracle can be queried through unified SQL interfaces. MongoDB and other NoSQL databases integrate with structured analytics. Each database maintains its optimization and security model while participating in federated queries. Specialized databases for time series, graph, or spatial data extend lakehouse capabilities. This approach avoids the complexity and cost of maintaining multiple analytical systems. Organizations leverage existing database investments while adopting lakehouse architecture. Technology-specific optimizations remain available while gaining integrated analytics benefits. Governance and compliance use cases address regulatory requirements for data locality and access control. Sensitive data remains in compliant locations while supporting analytics needs. Federation enables querying without creating copies that multiply compliance obligations. Audit requirements are met by keeping data in systems of record. Data sovereignty laws are respected by avoiding cross-border data movement. Access controls and source systems remain enforced during federated queries. Right to be forgotten requests only need execution in source systems. This approach simplifies compliance while enabling analytics. Regular compliance audits verify that Federation maintains required controls. Organizations meet regulatory requirements without sacrificing analytical capabilities. Documentation. Lakehouse Federation